So on page 3, we're going to look at another kind of asymptote that we'll be seeing, which is a horizontal asymptote. Now this one has nothing to do with domain restrictions. Looking at these pictures here, what we see is the other notation from that first page. We're now going to be referring to what our function does as x approaches infinity or negative infinity. These examples are all just looking at the direction of to the right, towards positive infinity. And the idea that these rational functions we're going to draw, they will have this almost like an end behavior that we've discussed before with polynomials. Only this end behavior won't just simply be an up or a down. It will be that the function gets closer and closer to a specific value of y. So you notice the equation y equals b representing this horizontal line because all horizontal lines have that form, y equals a number. And so we're saying b would be this value right here on the y-axis. And so the two possible options are your function approaching it from below or your function approaching it from above, right? Either way, the notation is the same. We don't use the plus or negatives of above and below here. But the idea is it's really you're looking at as x goes to infinity, this function gets closer and closer, again, to this specific number. Now, the difference, one distinction to make about these horizontal asymptotes is in this third picture where we see it is possible for our graph to cross this line. If we have a horizontal asymptote that's determining this behavior here, inside, or what you could call the middle of the function, it's absolutely possible for our graph to cross that line and have a value there. Again, this is different from domain restrictions where we just couldn't plug in an x. Here we're just saying, what's our function doing as x gets really, really large or really, really small if you're going to the left. So this behavior is really only about that end behavior, going to x going to infinity and to negative infinity. In the middle is fair game, and when we get to graphing, we'll discuss that. We'll discuss the question of whether it crosses. In fact, we will down here below with these examples we'll see in a moment. But that's it. That's what we're looking at, is that behavior. Now to find the horizontal asymptote, to find essentially that equation, that value of b, to find that line, this is the general form of our polynomials, our rational function. Both a polynomial in the numerator and denominator, both are going to have what we would call a lead term. And that lead term has both what we call the degree of the polynomial, that power on x, as well as a lead coefficient, the number out front. And so in this notation, I know there's a lot going on, but it boils down to determine the horizontal asymptote. The first thing you do is you look at this pair of exponents, your lead term exponents, or the degrees of the polynomials. So the labels of n and m, n for the numerator and m for the denominator, degree. And so that rule breaks down into one of three situations. If your n, your degree of your numerator, is smaller, right, less than the degree of your denominator, so if n is less than m, then we immediately know the horizontal asymptote is at y equals 0, or in other words, along your x-axis. Done. Hopping to the third one. If n is greater than m, if your numerator's degree is larger than your denominator's degree, there actually are no horizontal asymptotes to this graph. Now that does mean something else could happen, but we're not going to dive into that specifically. The other option though, if the two degrees are equal, right? If the two exponents there are equal, then you have to look a little further to find the horizontal asymptote. It will be at the line y equals, but then it will be the ratio of your lead coefficients. So when those two powers are identical, you create the fraction of those lead coefficients, and that value, whatever it is, number or fraction, that is the value that gives you the horizontal asymptote for your function, for your rational function. So with that said, let's take a look at three quick examples where we will do two things. We will locate the horizontal asymptote and then determine if the graph will cross. So again, this question of crossing is that idea of up here. Will it cross it somewhere in the middle, right? Somewhere in between, not at the ends where it is determining that end behavior. So for the first one, we look at our polynomials, and we don't need to look any further than this being an x to the first and that being an x to the second. So since 1 is less than 2, that's our n is less than m scenario. I can bring those rules down here. So since n is less than m, we immediately know our horizontal asymptote is y equals 0. So that's all we need to see to know that our horizontal asymptote, I'll abbreviate that HA, is that the equation of the line y equals 0. And notice, again, just like with vertical asymptotes, you want to write the equation of the line, not just say the asymptote is the number 0, it is the horizontal line y equals 0. Now, this question of does it cross? That question. What you're basically asking there, I'll go back to this picture, is you're saying we now know the location of this asymptote, this horizontal line. But if it crosses, if our graph crosses that line, then that means we would have to have our function have that y value as a value of the function. We'd have a point there, meaning some x would lead to that y value of whatever we're discussing. So in this first example, when we're saying that the horizontal asymptote is y equals 0, again, the x-axis, the question of does our graph cross that line is simply a question of can this function ever equal 0? Will it ever be 0? If so, then that's where it would be crossing this horizontal line. So we simply take the rational function and we create the equation of it set equal to 0. That's what we're asking. Will this ever be 0? And as soon as you write that, the next step is, first of all, clear that denominator. Well, clearing a denominator is simple enough. Just multiply by the denominator on both sides. Multiply left and right by that x plus 2, takes it out. So that leaves me with 3x on the left, still equals 0, because 0 times anything is 0. That's why I crossed that out, sorry. And so 3x equals 0 is an equation that we can solve. And we get x equals 0. Now what this means is two things. First of all, we asked the question, does it cross, by setting this equation up. And we were able to solve it. We were able to find an x value. So the answer to the question of does it cross is yes, it does cross. And we can say it crosses at a specific point, the point of x is 0, y is 0. So again, to answer that question, you simply take your function, you set it equal to 0, and you would see if that particular equation has a solution. All right? So we'll do a couple more examples of that so you can just see other ways this might play out. Example B here. Again, for the horizontal asymptote, we're going to be looking at first the n and m. Well, in this case, we've got 2 for both degrees, so that is n equaling m. Since n equals m, we need to create the equation right here. When n equals m, our horizontal asymptote will be at the line y equals, and then the ratio of those lead coefficients. Well, these lead coefficients on our x squareds are both 1, so 1 over 1. So we're looking at a horizontal asymptote of y equals 1. Now, with that asymptote, now the question of does it cross? Well, same idea. We take the original function, x squared minus 4 over x squared minus 1, and we set it equal to this number, right? Whatever the number that we're asking, will this graph ever have that as a y value? That's our question. All right, so I'm going to squeeze this in here. I want to get rid of that denominator, and that is x squared minus 1. So I'm going to multiply this left side by x squared minus 1 and the right side. So here, those take each other out and have x squared minus 4. Now on the right side, notice it's not gone. It doesn't cancel. That was because over here, that was 0 times that. Here you've got 1 times that, so you don't really need the parentheses to multiply that by 1 there, but we're left with that as a result on the right. Now you want to solve this, and what we can notice is we've got x squared on both sides, and if I go to move that x squared, subtract it from both sides, they're both gone. And I'm left with negative 4 equals negative 1. So variable's gone, variable disappears, and we're left with this statement. We've seen this plenty of times when solving equations. If you're left with a statement where your variables have disappeared and that statement is not true, right? Negative 4 does not equal negative 1. That means the original equation we tried to solve has no answer, has no solution. Now I'm not going to write no solution, but what I will say is if this equation were never true, then that's exactly the answer we want to our question, is that no, it doesn't cross the horizontal asymptote. because we were not able to find an x value for which it would, then that's the answer. The answer, does it cross, is no, it does not. All right, and our third example. We again are looking at m and n, and we see they are both the same, 2 equals 2. So we'll look at our lead coefficients. I'm just going to jump right to there. Y equals, so we've got a 3 and a 1. So our horizontal asymptote is y equals 3. Now the question of does it cross? So 3x squared minus x minus 6 over x squared plus x minus 6. The question of that equaling 3 is the question. So still, we will take both sides and multiply by that entire denominator, x squared plus x minus 6. I'll squeeze it in there and watch that cancel. Over here, x squared plus x minus 6. Now here, we've got that numerator on top. Here, we're going to distribute that 3. 3x squared plus 3x minus 18. Now, if I look at the 3x squareds, if I were to move both of those, they would cancel each other out. So that's convenient because now you know we're just working with a linear equation. We're not actually solving a quadratic equation of any kind at this point. So if this is all I'm left with is those x terms and numbers, I'll go ahead and say, let's move the x term that way and the constant term that way and get 12 equals 4x. Divide both sides by 4 and get x equals 3. Now, it is a coincidence that for both these examples in the notes that the x and the y have come out to be the same number. When we had it, y was 0, we solved x equals 0. Here we got y equals 3, and we're getting an answer of x equals 3. That is complete coincidence. Do not think that that's going to be the pattern or always happen. However, now that we have that number, we can say, first of all, yes, it does cross. And specifically, it crosses at the point of x is 3, y is 3.